All right, guys. Unfortunately, this is gonna be another 30-minute video, but we got Pidgey today. So I found this video, all 151 Pokemon real voices. That's dope. Thank you to this guy. I don't know why he made this, but I pulled up the Pidgey timestamp, so. Ah! Okay. Holy shit, dude. What a comments turned off. Amazing. All right. Dang, that's a flashbang. Let's do an assessment. We haven't done an assessment in a while. In 30 minutes. I have an hour, but like look, you have 30 minutes, so. Is this like backtracking? What is this? Dang, this is an interesting problem. Because I have no idea how to solve it. I think it's recursive, like it's some backtrack approach. But I have no idea how to do it. Oh, this is 0 index. This is 0, 1, 0, 1. This is 0, 1, 0, 1, 0, 1, 2, 1, 2. Okay, so that's how you're gonna do that. That makes sense. But how do I even want to like... Dude, I have no idea how to even start with this problem. Like, I think the approach I have right now is you start here, 0, or it's 1, you go to 2, and then you add these two. If one of the numbers is missing, then you know it's a 1. So this number is missing, so it's a 1. You go here, this number is missing, so you do a 1. But the problem is I don't know how to like go from this to access this. Okay, let's just try to get this structure going. Maybe that will help. Okay, and also, can this like GIF stop playing? Please. It's very annoying. Okay. Okay, for I in range of 0 to num rows. And we need 4j in range of... So it's len of num rows minus I to the len. Oops. Okay. Row dot append 1, and then r dot append row. And let's just print out r and return one of these. Let's just see what happens. Nice. Okay, we got that structure going. All right, and now, it's right here. The logic is right here. Okay, if else so we get the last one. Last row equals r at spot -1. So that's gonna get, like, if we're here, it's gonna get here. Okay. And then right? Song I was thinking about earlier today. I forgot how it goes. The tears. Guys, I got the stats midterm tomorrow. I'm nervous, bro. The class like seems easy, and I think it is, but I'm just like kind of lost for no reason. You know what I mean? It's one of those. Make me feel dumb and stuff. Okay, if is it -1? So this is 0. So it's -1. So if, whoops. So if j -1 is equal to -1, or j is equal to the, so if, hold on. So this is 0, 1, 0, 1, 2, 0. If j is greater than, so 0, 1, 2, no, if it's equal to the len of last row dot append 1, else row dot append something. So we need the 0 and the, yeah. Okay, wait, num last underscore row at spot j plus, oh wait, no, it's j -1. This is 0. So 0, 1. So we need the 0, and then we need, yeah. Row plus last underscore row spot j row dot append num. I think that's it. Just kidding. And I really screw up this. All right, print last underscore row. It should be going to this. J. Three. What? Three? Oh, wait. Is it because of that? It's 0 to I. Plus 1? Is that possibly it? That looks right. Nice. 10-minute. That was definitely an easy. Width of binary tree 4. What? Dude, I think I know what this is, and I think this problem is impossible. Like, it's a medium, but it's, like, impossible. All right. Binary tree, return the maximum width. Is the maximum width among all levels. The maximum width of a tree? One, two, three. No, that doesn't make sense. Did it stop at 7? Oh, it's where it stops. Is it where it stops? Because, like, it counts all of these, but it stops at 7. Right? The length between the end nodes. So, like, this one to this one. Okay. That's not... Okay, the length between the end nodes. The width of one level is defined as the length between the end nodes. Where the null nodes between that would be. That makes sense. Okay. That's tricky then. Because I don't really know... Excuse me? I mean, there's just like no shot of solving this in 15 minutes, but I'm going to give it a shot anyway. Trying to think if DFS or BFS would be better. If I like this in like level order, be like bing, bing, bing. One sec. All right. But it's a binary tree. Does that help me that it's a binary tree? Is it possible I can get... So this is like 0. I can do like 1, -1. And that'll be 2 technically, right? So 1, so 0, 1, -1. This would be -2. Yeah. So I think that's maybe what I'll do is I'll associate each node with like a distance away from, because this will be 0, 1, 2. This will be 0, 1, -2. And if you add the ABS values, you get 4. So this is 0, 1, 0. Because when you go right, you decrease. When you go left, you increase. Genius alert. Are any nodes equal in this tree? Are we allowed that? No, that's actually genius. Okay. So we're gonna need a thing with this, and it's gonna be level and then problem is this is gonna be super slow, but it's not slow enough for it to matter because that's and then distance. Okay, def DFS. We're gonna take the cur, the level, and the distance. Okay, if not cur, return. So DFS cur dot left, level +1, distance +1, and then DFS cur dot right, dude. Level +1, distance -1. And then we're just gonna add hashy at spot cur. Wait, no, hashy at spot. No, not level. It's cur. That's the problem with it. No, it's. I need a good way to store this. I have no idea how to store this. Okay, I think this works. Like what I'm trying to do is working, but after I process the data, like I get the level and the distance, I don't really understand because this doesn't work. This. Do I need an array of arrays? How many levels could there possibly be? 3,000? Can I have 3,000 arrays? Is that allowed? Because maybe I can just have each. Like I can have a 2D array. This is probably overcomplicating, but I can have a 2D array of like each array is corresponds to a level. So like level 0 is level 0, or array 0 is level 0. Okay, so we'll have R equals Boom. Okay, if len of R is less than level, then R dot append a tuple. No, not a tuple. I only need the distance. Distance. Else R at spot level dot append distance. Okay. Let's see if that works. So if level is 1 and this is 0. Oh, because it's like 0 indexed because it's stupid. Less than or equal to. Try that. Just want to see what happens. Oh wait, this is a different one. 13253. What is this -2? Oh, because it's not ordered probably. Or something like that. Hold on. Hold the phone. Hold it. Hold. Are you guys holding the phone? Something's not right here. Hold on. Len of R is 0. Level. No, because level's going to be 3. Can I do this first? Is this still out of range? Yeah. No, wait, this should just run though. This is correct though. This is right. Oh wait, no, it's not. Oh, no, it is right. I think. Let's try this one. Zero, one, -1, 0, 1, 2, 0, 1, 2, 0, 1, 2, 3. How the hell is it 7? No, that makes sense. Wait. No, wait, that doesn't make sense. One, two, three, four. Wait. 1, 2, 3, 4. How is it 7? The maximum width exists in the 4th level. 6, 1, 2, 3, 4, 5, 6. Oh, because this isn't 1. This is 1. That counts all of these ones. God dang it, dude. I felt that solution was gonna work. Zero, 1, 2, 1. It's missing all of these 2, 6. Wait, what? What's these? There's 1 right here. And then that's 1, 2, 3, 4, 5, 6. Wait. 1, 2, 3, 4, 5, 6, 7. Yeah. Gosh. I have no idea how to take into account these nulls. Like, I have zero idea. Because this is neither. Wait. 1, 2. 1, 2, 3. It's 4. It's not even 3. It's 4. If I get 0, 1, 2, 3. Oh, no, 0, 1, 0, 1, 2. I have no idea. I don't know how to count the nulls. How do I count the nulls, bro? Like what do I do to count them? Art spot level dot appended. Man, I was really feeling that, dude. I was really feeling that was gonna work. But it doesn't. It's like exponential. It's like this is 1, this is 2, and then this is 3. But it's minus 1, so it's 2. So 1, no, it's 3. There's something wrong with this like formula. Like I bet if I adjusted this formula somehow, it would work. You know what I mean? But I'm like running out of time. I like really have to look at the solution here. Unfortunately. I mean, this is like also level order. Max is replaced. Like, who are you, bro? Get a job. Get a job. Well, I probably shouldn't show the LinkedIn. All right. No, I don't really got much going on. Oh, Neatcode has a video on this.
Hey everyone, welcome back, and let's write some more Neetcode today. So today let's solve the problem maximum width of a binary tree. We're given the root of a binary tree and we want to return its maximum width. Well,
it's this. 2 times L plus 1. Should I try that? Let's try it now. Okay, well, that's not really. Wait, that's not doing what I needed to do at all. 1, 1. Is it plus 1 too? That doesn't make sense. 7, 7. Oh, you just 2 times L. And curd out right is... Wait, 2 times level? Wait, what? What is this L? Yeah, that's the thing. We should start level 1. 2 times level. 2 times L plus 1. At this point, I'm just like...
What is its maximum width? Well, it's a bit different than what you might expect. Taking a look at this binary tree, this level, you might expect it has a width of 4. Basically, it's measured as taking the leftmost non-null node in the level and the rightmost non-null node in the level and getting the distance between them. And in this case, the distance is measured by each spot where a node could go. Like here, there is a node, but we know that there could also be a node over here. So that makes this distance of length 4. So even though there's 3 nodes, we say that the width of this level is 4. So that makes it a bit trickier than you would think by just using like a simple algorithm like breadth first search, because with tree problems, those are usually our 2 choices. We can either do DFS, depth first search, or BFS, breadth first search. In this case, since we are trying to get the width of a level, BFS does seem more intuitive, but it's also not quite as straightforward as you might think, because with breadth first search, the answer that this would give us for the 3rd level here is 3, but we would actually want a 4. Now, otherwise, breadth first search is pretty good because what it will do is it will go level by level, allowing us to get the width of each level, because we don't necessarily know that the last level will have the widest width, so we have to do so for each level. But the question is, how do we count these empty positions? Let's take the same tree structure as this example. You might first try taking this node and adding it to a level, okay? Then add its children to the next level, and then take these 2 nodes and start adding their children to the next level. Let's say that this 4th level is the one we're paying attention to right now. Here, since we want to be able to count 1, 2, 3, 4, let's try adding null to the queue. So even though this guy's left child does not exist, we can try adding that to the queue as well as adding this real one. Then when we start popping from the queue, we'll count 1, 2, 3, 4, and it'll give us the accurate count. Now, the problem here is if this guy doesn't have a child, then this guy will also not have children either. But for the subsequent levels, we do want to get the accurate count. So this is a method like we technically could do for null. We could also add null to the queue or its children, but this is going to get complicated and a pain to code up, but we can use a similar technique here to count these null nodes. And the idea is reminiscent of how heaps work. With a heap data structure, each node is actually numbered starting at 1, and the number assigned to its left child is always 2 times what its value is. So the left child is going to be 2, and the right child is going to be 2 times that plus 1. So it's going to be 3 here. And this guy's left child is going to be 2 times 2, which is 4. And I'll just quickly fill in the rest of this structure. The right child here is going to be 2 times 2 plus 1. That's 5. Left child here is going to be 6. Right child is going to be plus 1, 7. And we could continue building out the tree structure just like this. But how does this help us? Well, ideally, we would be able to assign each node in the tree a value corresponding to its position. Then, even if a node like this one doesn't exist here, we will still count the width of this level as being 7, the value assigned to the rightmost node, and 4, the value assigned to the leftmost node. We'll take 7 minus 4. that's 3. We'll always do a +1 because that's just how calculating the length works. So now our result will end up being 4 for this last level. So that's the idea. Now, how exactly are we going to implement it using breadth first search? Well, it's pretty simple. We're going to have our queue data structure. We're going to add the root to the queue, which is 1. We're also going to assign this node a number, and the root is always going to be starting at value 1. So this is going to get confusing because we have multiple numbers, but I'll just show you. The first one is going to be the node. The second one is going to be the number assigned to that node. And the third one is going to be the level for that node. In this case, for level, I'll just say it's starting at 0, though we could say this is the first level. The level doesn't really matter, but it's going to be used for us to distinguish when we're at this level and then we move to another level. So let's say the level is 0. Then when we pop from our queue, we get its 2 children and add those to the queue. So we would add 3 to the queue and we would add 2 to the queue. I'm just putting the values themselves. Just assume we're also adding the number and the level, but for this node, its number would be 2 and this guy's number would be 3, even though that's like the opposite of like their actual values. But you can see getting the number of a node is as easy as just incrementing. If this guy starts at 1, this is going to be 2, this is going to be 3, 4, 5, 6. Pretty simple to get the number, and the level is also going to be pretty easy because when we take the children of this guy and append them to the queue, we're also going to say, well, if this is level is 1, this is level is going to be +1, so it's going to be 2, or wherever we start at. If this was 0, this would be 1. And lastly, to actually get the width of a level, anytime we get to a node that is the first node in that level, we will know because we have just popped it from the queue and its level is different than the previous one. So we'll be able to automatically detect that, and we will always know the first node in a level. So then when we get to every other node, we will easily be able to calculate the width because we only need the first node in the level and whatever the last node in the level is to calculate the width. Since this is just a BFS algorithm, we are going to code this up in big O of n time, where n is the size of the tree.
I think I get it.
Memory complexity. So now let's code it up. So the first thing I'm going to do is initialize our and root node, its level. So
what is it? 0, 1? 1, 0.
So I'll add a con is going to be the number assigned to it. And 0 is going to be its level. So I'll add a comment just to make it more clear into it. And while the queue is non-empty, we are
Okay, hold on. While Q I in range.
are going to want to pop from the queue. So we're going to say queue pop left. We get 3 values: the node, the number of the node, and the level. Of the node. Now, how do we update the result if we wanted to? Well, we would want to set the result equal to the max because we are trying to find the maximum width. We would take the max of itself and we would calculate the new width. How do we do that though? Remember, I was talking about taking the number of the current node and subtracting it from the first node in the same level. So we have to keep track of the level. How do we even update the level? Well, if we ever got to the point where the current level was greater than the previous level, then we would set the previous level equal to the current level. The current level wouldn't really change, because it's going to be updated on each iteration of the loop. Well, first of all, we're going to need a new variable for this, so I'm going to do that over here. We're going to keep track of what the previous level is, and we're going to keep track of what the previous number is. This actually should be called the number of the first node in the current level, because that's what it's going to be used as. I'm going to initialize both of these. Well, the level we'll say is going to be 0 to start out with, and the previous number, I guess, is also going to be 0. It should be 1 less than whatever our first node's number is for the math to work out. But here where we are updating our previous level, let's also set our previous number equal to the current number. So this means anytime we update our level, the number, the previous number, will always be set to the first node's number in that level. That's exactly
What is
we
this guy
want.
talking
Because
about?
now when we calculate the width of the current level, we can say the current number minus the previous number plus 1. This is our offset that we're always going to include. And there we have it. We have updated our result. The only thing you don't want to forget is for the node, we also have to add its children to the queue. But we're only going to add the children if they are non-null. So I'm going to check, is the left node non-null? If it is, then we are going to append it to the queue as like a sublist or a little list with 3 values. The child itself, node.left, as well as the number of the node.
I don't understand
the
this way of doing it.
is always going to be 2 times the current number. And the level, which is always going to be plus 1 of the current level, since this is a child of the current node, its level, of course, has to be plus 1. And we're going to do the same thing pretty much for the right child.
I like this
as
way
well.
better.
The one thing I will mention, though, is make sure you append the left node before.
Yeah, screw all this noise, bro. Wait for. I think he calls it L. Yeah. Okay, and then it's. I guess it's actually probably smart to do it like this. With a tuple instead. And then what's the, is it the equation goes here? Cur.left 2 times. It's not level, it's num. It'll be better to do it like that. And then if cur.right, q.append, cur.right 2 times num plus 1. Right? Yeah. Oh, it needs to be a thing here. It needs to be a tuple. Wait, and then if len of q is greater than 1, because it's not the... Oh, yeah, that makes sense. What math are you doing here? Q at -1 minus q at 0. Okay, I don't really understand this part of the thing. Cannot unpack non-iterable object. Can't. Let me just make sure. Let me just do this real quick. Just make sure that this is actually like it works. Oh, it does work. Wait, what? Q equals deck. Oh. Is it like... What did he do? Root 1. There we go. Oh! Hmm. I don't really understand like this like... I gotta go to sleep, dude. I'm so tired. I don't really understand this like magic right here. The last number in the queue. The first number in the queue. Oh, because I'm popping. Oh. Oh, I'm popping. Oh. No, it makes sense. Okay. That's interesting. I like that. Damn, we're so close to 200. I want to get to 200 so bad, dude. It'll be dope when I get to 200. All right.